This video clip is for us to take a look at what's known as ionization energy. This is objective number 21 in our current unit of study. Specifically, we're going to take a look at the first ionization energy. Ionization energy refers to the energy required that'll take an electron away from a neutral atom and turn that atom into a +1 ion. So our ionization energy, the first ionization energy, is this energy that's required to strip an electron away from a neutral atom and turn that atom into a +1 ion. If we examine a table of first ionization energies, we can see a relationship between the first ionization energy and the position of an element on the periodic table. Let's take a look at these trends and why these trends exist for first ionization energy. If we take a look at the ionization energy of lithium as we go from lithium across the periodic table, moving from lithium across to neon, we can see the general trend here is that ionization energy goes up as we go from lithium across the periodic table until we get to the element neon. We can see a similar trend for each row or period on the periodic table. As we progress from sodium to argon, moving across the periodic table, we can also see that our ionization energy goes up. Similarly, as we move from potassium across the periodic table to krypton, we again see that our first ionization energy increases as we move across the periodic table. The general trend we can see from all of our first ionization energies is that we go across the periodic table, the first ionization energy is going to increase from element to element as we move across the periodic table. A different trend appears as we move from lithium to cesium going down the periodic table. From our data for first ionization energies, we can see as we move from lithium to cesium, there's a general trend of the first ionization energy becoming less and less. So the pattern we can see as we go down the periodic table, going from lithium down to cesium, the general trend that we can observe is that the first ionization energy becomes lesser. So the general trend that we have, again, as we move down the periodic table, in this case looking at the first column from lithium down to cesium, we notice the first ionization energy decreases. We have two trends on the periodic table. Once again, as we go across the periodic table, we've noticed our first ionization energy increases, and that as we go down the periodic table, the first ionization energy becomes less and less. Let's take a moment now and explain why this trend exists for first ionization energy. Starting out, we'll focus on the pattern from lithium to neon as we go across the second period of the periodic table. There's two things for us to take a look at. One is in the second row on the periodic table, all the elements exist in the second principal energy level. We're all at n equals 2 for the energy level of the outermost electrons. The second thing is for us to focus on how many positive charges or protons are located in the nucleus of each of these atoms. Starting with lithium, we have 3 protons and a charge of +3. By the time we get to neon, we now have 10 protons and a +10 charge in the nucleus. A formula that will be of use for us is Coulomb's law, which gives us the force of electrostatic attraction between charged particles. Another trend that underlies our reason for the general trend in ionization energy is that we go across a row on the periodic table, the atoms tend to get smaller and smaller as we move across. The reason the atoms get smaller is due to Coulomb's law. If we look at lithium, lithium's nucleus has a charge of +3, and it has a total of -3 from the 3 electrons. The electrostatic attraction from a +3 -3 interaction is much smaller than what we see for neon, where neon's nucleus has a charge of +10 a total of negative 10 from its electrons. Q1 and Q2 in this formula represent the size of the charge. The stronger the charge, in this case neon, plus 10 minus 10, means the force of attraction between the nucleus and the outer electrons is going to be strong, fairly strong, causing the outer edge of the atom to shrink in towards the nucleus, relative to what we see in lithium, where with a plus 3 minus 3 total charge, the amount of attractive force between the nucleus and the outermost electrons is lesser. Therefore, lithium is a larger atom than what we see for neon on the opposite end of the periodic table. What we see as we progress across the periodic table, going from lithium to beryllium to boron to carbon, all the way over to neon, is a successive increase in the number of protons in the nucleus, along with a successive increase in the number of electrons in the electron cloud. Because we're still at energy level 2, the charge of that nucleus interacting with the outer electron cloud, the charges are getting greater and greater, so the force of our attractive force gets stronger, so the nucleus is holding on to the electrons with an ever stronger and a stronger attractive force as we progress across the periodic table. Keeping in mind that the first ionization energy is the energy required to remove an electron from a neutral atom and turn the atom into a +1 ion, as we go across the periodic table, the nuclear charge is getting greater, so the nucleus is holding on to the outermost electrons with an ever larger force of attraction. Given that the force of attraction is greater as we move across the periodic table, the energy required to remove an electron becomes greater and greater. And it's this increased nuclear charge interacting with the outermost electrons that causes the force of attraction to increase, that creates our trend in ionization energy that we see as we go across the periodic table. The ionization energy is going to increase. A different trend emerges as we progress down the periodic table, and that we go down the periodic table, the amount of energy to remove an electron becomes less and less. As we go down the periodic table, as we move from lithium to sodium, what happens is we've moved to the next energy level. The outer layer of electrons in sodium are at energy level 3 for the 3s sublevel. And when we go to potassium, the outer level of electrons is now at energy level 4 in the 4s sublevel. By moving down the periodic table and adding on successively higher and higher energy levels, the atom's getting larger and larger. Consequently, the distance between the nucleus and the outermost electrons is getting larger. If we can look at Coulomb's law equation again, because distance here and its distance squared is in the denominator, as the value of distance gets larger, it's going to cause the force of attraction to get smaller. So in this case, as we're moving down the periodic table and we add on successively higher and higher energy level orbitals, the atom's getting larger, which causes the distance between the nucleus and the outermost electrons to increase, which causes the overall force of attraction to go down. So what we see is with this distance between the nucleus and outer electrons increasing, the force of attraction decreases, so our energy required to remove an electron from a neutral atom to turn it into a positive ion becomes less and less. And this would account for the trend that as we go down the periodic table, first ionization energy becomes smaller. Another factor that comes into play is that we have lower energy levels that are completely filled. In the potassium atom, energy level 2 is full, energy level 3 is full, and these full inner energy levels shield the nucleus somewhat from the outer electrons, diminishing the overall influence of the nucleus on the outer electrons. Because the attractive force of the nucleus is diminished by this shielding of the filled inner energy levels, that also causes the overall force to become less, and a lesser force means less energy is required to pull out an outer electron. This is specifically known as the shielding effect, where the overall charge of the nucleus is slightly diminished on the outermost electrons by the inner orbitals being full and blocking some of that positive charge of the nucleus. If we notice in our trend of ionization energies, there's two locations where there's a slight kink in the pattern, where the energy drops slightly instead of increasing. Let's take a look at why that occurs. The first kink in the pattern occurs as we move from beryllium to boron. We can see that as we move from beryllium to boron, the ionization energy actually goes down slightly. For this explanation, we need to take a look at the orbital diagrams that we have for the electrons. As we add in the last electron for boron, we notice it's the first electron located in the 2p sublevel. We note here the 2p sublevel is at a slightly higher level of energy than we see for the 2s sublevel. Because the 2p is now slightly further away from the nucleus, this single 2p electron is easier to extract than breaking apart the pair we have here in the lower energy of our 2s electron to remove that. That's why we see this kink in the pattern as we go from beryllium to boron moving across the periodic table. The second kink in our pattern occurs as we move from nitrogen to oxygen. This would be, if we look at our orbital diagrams again, there's something unique happening here. In nitrogen, each 2p orbital has one electron in it. Whereas when we go to oxygen, the first of the 2p sublevel orbitals now has a pair of electrons. The pair of electrons here are a negative and negative charge. Those negative charges of that pair repel from each other, and the energy of the repulsion between the pair of electrons make it so that it's easier to reach in, pluck one of those electrons, and pull it away from the nucleus, which is why we see this kink or drop in ionization energy as we move from nitrogen to oxygen going across the periodic table. It's because of that repulsive force between the pair of electrons. As we move to fluorine, the additional proton in the nucleus starts to overcome the repulsive forces of the paired electrons, and we see that the ionization energy continues in an upward trend. Finally, when we get to neon, we have all the electrons in the energy level are paired, the energy level is full, this is very stable, and the energy required to remove an electron from neon becomes very high. Let's do a quick recap. Moving from beryllium to boron, we experience the first kink in our pattern, and that occurs because in boron, the first electron we see in the 2p sublevel is at a higher energy than we see for the 2s. Because it's at a higher energy, it requires less energy to extract and pull that electron away from the nucleus. Therefore, we see a drop in the ionization energy. Second kink in our pattern occurs between nitrogen and oxygen, and this happens as we move from nitrogen to oxygen. We have our first pair of electrons in the 2p sublevel, and the negative to negative repulsive force between the pair of electrons is sufficient that it's pushing the electrons apart with such force that it's easier to now come in and remove an electron, causing the ionization energy to drop slightly as we go from nitrogen to oxygen.